last two classes we are studying about the 2 degrees of freedom system. So, in these cases we have studied about the physical coordinate system, generalized coordinate systems and principal coordinate system. In case of physical coordinate system, you are taking a set of coordinate systems and finding the physical parameter or coordinates of the points of which you are finding the equation motion. In case of the generalized coordinates, so these are the set of minimum number of coordinates required to express the motion of the system, and in case of principal coordinate system, you are taking a coordinate system in which your mass matrix and stiffness matrix are uncoupled. So, you have studied about this physical coordinate system, generalized coordinate system and principal coordinate systems. Also, I told you about the derivation of equation motion using Lagrange principle. So, in case of Lagrange principle, you are finding the kinetic energy of the system, the potential energy of the system, and you are using this formula, that is d by dt of del t by del qk dot minus del t by del qk equal to this capital Qk. This capital Qk is the generalized coordinates. So, where this generalized coordinates equal to I equal to 1 to n. So, if you have n number of, or your system contains n particles, so it will be I equal to 1 to n. So, your Qk equal to I equal to 1 to n f I dot del Ri by del Qk. So, where this Ri is the physical coordinates of the system and Qk is the generalized coordinate of the system. So, you know that this, if you have I number of physical coordinates and k number of generalized coordinates, then this I and k can be related like this. So, I will be equal to, so number of physical coordinates will be number of generalized coordinates for plus the number of constants. So, let constant I am writing m. So, m is the number of constants of the system, then this m is the number of constant. So, using this number of constant and the generalized coordinates, so this is the physical coordinates. For example, in case of a, so you just take the case of a double pendulum or a single pendulum, in this case you just take. So, in case of a single pendulum, the physical coordinates are x1, y1 and your generalized coordinate is theta. So, this theta, so your k equal to 1 and here physical coordinates your I equal to 2 and number of constant, that is equal to m equal to 1. So, this constant is nothing but your x1 square. So, the length is constant. So, this x1 minus 0. So, this point has a coordinate of 0 0 you can take. So, x1 minus 0 square plus y1 minus 0 square will be equal to this length square. So, or your L will be equal to x1 square plus y1 square root over. So, you have one constant, that is the length of this pendulum. So, that is the constant. So, you have m equal to 1, k equal to 1 and I equal to 2. So, you can have the relation between these number of physical coordinates and the generalized coordinates by using the number of constants. So, previously I told you about the Lagrange principle. Using Lagrange principle, you can find the equation motion. Either you can use this from this kinetic energy and this generalized force, you can find the equation motion, or you can use the Lagrangian of the system, which is equal to L equal to T minus V. T is the kinetic energy, V the potential energy. So, you can use this expression to find the equation motion. For a system with damping, you can use this dissipation energy to find the equation motion. Also, you can find the equation motion by using this extended Hamilton principle. In case of extended Hamilton principle, you can use this expression, that is del L plus integral T1 to T2 del L plus del WNC dt equal to 0, where this del Qk are T1 equal to del Qk or T2 equal to 0, where del Qk is the virtual displacement of the system. So, virtual displacement of this generalized coordinates equal to 0. So, you may note that this generalized coordinate may or may not have any physical meaning, but they are the minimum number of coordinates used to define the motion of the system. Also, we have studied about the normal mode of vibration of a system, and already I have found the equation motion for these systems. I have taken a system, this simple spring mass system in which another rod is hanging, and I have found the equation motion using Hamilton principle. Also, you may use the Lagrange principle to find this equation motion. Already you have found for this same system, you have found the kinetic energy of the system equal to this half m x dot square plus half m Vc into Vc. C is the mass center of this rod plus I c theta dot square. Last class we have studied this equation. So, already you know the potential energy of this system. Potential energy is the potential energy of the spring plus the potential energy due to the change in height of this rod. So, after knowing this kinetic energy and potential energy, you can write the Lagrangian of the system equal to T minus V. Now, to find the q, k, n, c, that is q1 and q2. So, you can find this q1 and q2. So, in this case you can take your q1 equal to x small q1, this is the generalized coordinate, q1 equal to x and q2 equal to theta, and so your q1 nc. So, in this case already you know in the fast mass there is no force acting on the system. So, in this fast mass there is no force acting, and here you have a horizontal force acting. So, your F1 equal to 0 and F2 equal to this Fi. So, I am taking a unit vector in this x direction as I. So, F2 equal to Fi and F1 equal to 0, and the position vector of this point already you know. So, this is equal to r0 plus x. So, r0 plus x plus L. So, this is L sin theta. So, plus L sin theta I. So, you can write. So, you can write your r equal to. So, r already you know. So, this is your r2. So, r2 will be equal to r0 plus x plus L sin theta I minus L cos theta j. So, this is the position vector of. So, position vector of that point where the force is acting. So, you can find this q1 nc. So, qk nc. So, to find the non-conservative forces of the system. So, qk nc will be equal to. So, if you apply the formula, so this is equal to I equal to 1 to 2. This is Fi dot del Ri by del qk. So, you can. So, as F1 equal to 0 and F2 equal to. So, your F2 equal to Fi. So, you can substitute it in this equation. So, your R1. So, this is expression for R1, and as there is no force acting on the mass 1. So, F1 into del Ri del R1 by del Q1 will be equal to 0, and plus F2 into del R2 by del Qk will be equal to. So, you can find that expression. So, you can find this Q1 Nc will be equal to summation I equal to 1 to 2, or directly you can write this way. So, you can write this is equal to F1 dot del R1 by del Q1 plus F2 dot del R2 by del Q1. So, this will be equal to. So, this as F1 equal to 0, this first part equal to 0, and the second part. So, already you know the expression for R2. So, where R2 equal to R0 plus x plus L sin theta I plus or minus. So, it is equal to minus L cos theta j. So, if you differentiate with respect to this q1 equal to x. So, q1 equal to x. So, you differentiate. So, this becomes 1. So, this becomes I. So, this is equal to Fi dot I. So, this becomes F. So, already you know that your fast force. So, the force equal to q1 nc equal to F. Similarly, your q2 nc you can find. So, this will becomes F1 dot del R1 by del Q2 plus F2 dot del R2 by del Q2. So already you know your Q2 equal to theta, F1 equal to 0. So as F1 equal to 0, this first term equal to 0 and second terms will give you, so this is equal to Fi dot del Ri by del Qy if you find. So already you know your R2 equal to, so as R2 equal to R0 plus x plus L sin theta I plus or minus L cos theta j. So differentiation of this with respect to theta, so these two terms 0 and this will give you, so this is L sin theta, so differentiation of this equal to L cos theta, so this is into L cos theta I minus, so minus minus plus, so L sin theta j. So from this you can find, so from this you can write, so this becomes equal to, so this j I dot j equal to 0 and I dot I you can take, so this becomes FL cos theta. So the second force, second QK NC equal to FL cos theta and the first one equal to F. So you can write the equation motion by using the Lagrange principle, that is d by dt of del L by del. So for the first equation you can write del L by del x1 dot minus del L by del x1. So this will be equal to your Q1 NC and second equation will becomes d by dt of del L by del x2 dot minus del L by del x2 equal to Q2 NC. So using these two expression, so you can find the equation motion is this. So the first equation motion is reduced to m plus m x1 double dot plus half ml theta double dot cos theta minus half ml theta dot square sin theta minus kx equal to f, and the second equation becomes 1 by 6 ml 3x double dot cos theta minus 3x dot theta dot sin theta plus 2l theta double dot plus half ml x dot theta dot plus g sin theta equal to FL cos theta. So you have seen, so these are the generalized coordinates we have obtained. So these are the same equations what you have obtained using this extended Hamilton principle also. Also last class I told you about the normal mode of vibration. So normal mode refers to the motion of the system in which all the particles of the system have or are moving with same frequency and passing the equilibrium position at the same time. So using these normal modes, last class we have also found the free vibration response of a system and normal mode vibration. So using the normal mode vibration, so for this case we have taken the double pendulum. So in case of double pendulum, we have derived the equation motion using Lagrange principle, and from that we have found the normal modes of the system. So in case of normal, so we have found two normal mode vibration. So one we got lambda 1 and lambda 2. So two frequency we obtained, and taking those two frequency we have obtained the normal modes of the system, that is theta 1 theta 2. So we obtain theta 1 theta 2 at lambda equal to lambda 1 and theta 1 theta 2 at lambda equal to lambda 2. So these are the normal mode vibration of the system. So in the first case we have seen, so in the first normal mode we have seen that the two masses are in phase, and in the second case the two masses are out of phase. So now let us derive the same expression or derive for the same simple double pendulum. So let us take this double pendulum and derive the equation using another coordinate system. So that is, if we will take the coordinate system as x1 x2 instead of this theta 1 theta 2. So I will use the other method, that is the Newton's method, to derive this equation motion. So in this case let me take the generalized coordinate as x1 and this generalized coordinate as x2. So as you know, this x1 y1 x2 y2 and this theta 1 theta 2, they are related, or if I am taking this theta 1 theta 2 as the generalized coordinates as these lengths are constant. So I will have two constants equation, that is length of this is constant and length of this is also constant. So I can have two constant equation. So this x and y, x1 and y1 are also related, and this x2 and y2 are also related. So I can take this x1 and x2 as the generalized coordinate systems also in this case, and by taking this generalized coordinate system instead of taking this theta 1 theta 2, I can also derive this equation motion. So let us derive this equation motion using the Newton's method. So this is theta 1 and this is theta 2. So this is mass m1, this is mass m2, this length is L1, this length is L2. So let me draw the free body diagram to derive this equation motion. So derive this equation motion using Newton's method. So I have to draw the free body diagram of this mass and this mass. So for this mass m1, so let me draw for mass m2. So this is mass m2. So the forces acting on this mass m2 are this weight is acting downward. So this weight is m2g, and the other force what is acting on this system is its tension T2. So I can take this m2g and this tension to find this equation motion for this system. So I can take a coordinate system, xy coordinate system, this is x direction I can take. So this is the x direction, this is the y direction, and as this second link make an angle theta 2 with this vertical line. So this angle will be equal to theta 2. So this angle is theta 2, and so I can write, resolving these forces, I can write the equation motion. So the other force acting on this system is the inertia force, that is as it has moved a distance x2, so the inertia force will be acting in opposite direction. So that magnitude will be m2 into x2 double dot, but it will act in a direction opposite to the direction of acceleration. So this becomes m2 x2 double dot. So now I can resolve the forces in vertical and horizontal direction, and I can write the equation motion. So the equation motion in this case, or in this case if I write the force balance, if you will do the force balance, then you can see that this force, the component of this force in this vertical direction, that is T2 cos theta 2 will be equal to m2g, and T2 sin theta 2 plus m2 x2 double dot will be equal to 0, or I can write T2 sin theta 2 equal to minus m2 x2 double dot. Now I can draw the free body diagram of this mass m1. So for this mass m1, the forces acting, so this is the vertical line, this is the horizontal line, I can, so this is the x direction, this is the y direction, and this is the tension. So this is theta 1, so this angle is theta 1, and I can write, so this is theta 1 and the other one will be theta 2. So I can write an other force, that is, so this is tension T1, and I can write this is tension T2. So this T2 makes an angle theta 2 with vertical, and T1 makes an angle theta 1 with the vertical. So as I have taken x2 as the generalized coordinate for this mass m2, so I can write the inertia force which is acting opposite to the direction of acceleration as m2 x2 double dot. So in this case, if I will do the force balance, then so these are the forces acting on the system. Another force, that is the weight of the system, that is m2g, is also acting on this system. So by doing the force balance, now this T1, this force, this T1 sin T1 cos theta 1 minus T2 cos theta 2 minus mg will be equal to 0. If I am writing the forces in the vertical direction, so I can write this T1 sin T1 cos theta 1, so T1 cos theta 1 minus T2 cos theta 2 minus m2g will be equal to 0. So, this is one equation, and the other equation in this horizontal direction will be t1 sin theta 1, t1 sin theta 1 and minus. So, this becomes t2 sin theta 2. So, t2 sin theta 2 I am taking, okay. So, this direction I have taken positive. So, or I can write this direction positive. So, I can write this plus, this minus, and minus m2 x2 double dot equal to 0, or in the other word I can write t1 sin theta 1. So, if I take a negative sign, this becomes negative and this will becomes positive. So, t1 sin theta 1 minus t2 sin theta 2 plus m2 x2 double dot equal to 0. So, if we will assume some small motion, that is theta 1 equal to theta 2 tends to 0, or they are very small. So, in that case I can have this cos theta 1 equal to 1, cos theta 1 equal to 1, cos theta 2 also will be equal to 1, and this sin theta 1 will be equal to theta 1, and sin theta 2 I can write it equal to theta 2, or I can write. So, you can see from this theta 1. So, this is sin theta 1 or equal to tan theta 1, sin theta 1 will be equal to tan theta 1. So, this will be equal to, or this theta 1 will be approximately will be equal to x1 by L, and theta 2 will be equal to, so this is theta 2. So, this will be equal to this distance by this L2, sin theta 2 will be equal to x2 minus, so this is x1. So, this becomes x2 minus x1 by L. So, substituting this, so from this equation you can see that this T2 will be equal to m2g. So, as theta 2 is very small, then T2 equal to m2g, and this T2 theta 2 will be equal to minus m2 x2 double dot, or I can take it this side. So, I can write this m2 x2 double dot, and already I know that T2 equal to m2g and theta 1 equal to x by L. So, using these expressions I can write. So, from these 4 equations, so you can write that this T2 equal to, so T2 already you got equal to m2g, and T1 will be equal to, so from this expression you can see that T1, so T1 cos theta 1, so this is equal to 1. So, this will be equal to m2g plus T2. So, T2 cos theta 2 equal to 1. So, already you know your T2 equal to, so this is for the first mass equation for the first mass, this is not for the second mass. So, in this case it is equal to m1 x1 double dot, m1 x1 double dot. Previous case you have m2 x2 double dot. So, for this first mass it is equal to m1 x1 double dot, and so this is equal to T1 cos theta 1 minus T2 cos theta 2, this is equal to minus m1g. So, this is equal to this weight equal to m1g. So, this becomes as T2 equal to m2g. So, this becomes T1 becomes m1g plus m2g. So, this is equal to m1 plus m2g, m1 plus m2g, and already you got T2 equal to m2g, and from the previous equation also you can find this m1 x1 double dot. So, now you substitute all the expression here. So, this becomes m1 x1 double dot. For T1 already you know the expression equal to m1 plus m2g, and sin theta 1 equal to x1 by L, and minus for T2 you can write it is equal to m2g, and the sin theta 2 already you know equal to theta 2, that thing equal to x2 minus x1 by L2, so into m2g. So, this is x2 minus x1 by this length I have taken L1. So, this become x1 by L1, this theta 2 becomes this by this. So, this becomes L2. So, in this way, so you can got the expression for this. So, this is equal to m1 x1 double dot plus m1 plus m2g x1 by L minus m2g x2 minus x1 by L2. So, by rearranging this equation, so you can write the equation in this form. So, this equal to m1 x1 double dot plus M1 plus M2 G by L1 plus M2 G by L2 x1 minus M2 G by L2 x2 equal to 0, and the second expression from this equation you can write the second expression, that is M2 x2 double dot plus for T2 you can write equal to M2 G into this expression. So, for the second equation you can write M2 x2 double dot plus M2 G x2 minus x1 by L2 equal to 0. So, you can express these two equations in terms of matrix form also. For simplicity, let us take this M1 equal to M2 equal to M and this L1 equal to L2 equal to L. So, I can write these two equations in terms of the matrix form. So, this matrix forms will give like this. So, this becomes M1 0 0 M2 x1 double dot x2 double dot plus, or I can write in the matrix form by substituting that expression. So, it will becomes 1 0 0 0 1 x1 double dot x2 double dot. So, this becomes 3 minus 1 1 into G by L into G by L into x1 x2 equal to 0 0. So, in this way you can get the equation motion of the system. Now, proceeding in the previous way, you can find the normal mode vibration of the system. In case of normal mode vibration, both the masses, this M1 and M2 will move with same frequency and will pass the equilibrium position at the same time. So, this is the normal mode we are assuming, and the actual vibration or actual free vibration will depend on the initial conditions. That thing already we have seen. So, now I will tell you another method to determine this free vibration response of the system. So, let us take a general, or we can determine the normal modes from the eigenvalues of the system. So, let us take a general 2 degree of freedom system. So, you can write the general 2 degree of freedom system in this form, in matrix form, that is mx double dot plus kx equal to 0, where m is the mass matrix and k is the stiffness matrix. So, you just take the m inverse, multiply, pre-multiply m inverse. So, m inverse m x double dot plus m inverse k x will be equal to 0, and this m inverse m is nothing but I x double dot plus, so m inverse k, let me write it equal to a. So, a x will be equal to 0. So, if I will substitute this x, so this is small x I can write. So, this vector small x, and so this is kx and this is small x, these are, so I can write in this form. So, the small x I can assume it equal to capital X e to the power I omega t. So, if I will assume in this form I omega t, or if I am assuming the normal mode vibration, that is all the masses are moving with same frequency omega. So, if I will substitute this in this expression, so this x double dot will reduce to, so x double dot will reduce to minus omega square x small x. So, this equation will reduce to a minus omega square. So, a minus omega square I into x will be equal to 0, or if I will substitute this omega square equal to lambda. So, I can write this equation as a minus lambda I x equal to 0. So, a minus lambda I x equal to 0, this x I can write x e to the power I omega t. So, this becomes a minus lambda I x equal to 0. So, already you know this is a familiar equation of eigenvalue problem. So, in this case you can obtain this lambda by finding the eigenvalue of this matrix A, or you can find the eigenvalues, or you can find the frequencies from by finding this a minus lambda I, determinant of a minus lambda I equal to 0. So, for this double pendulum already we know that the mass matrix equal to 1 0 0 1. So, for this double pendulum I can write this, for the double pendulum I can write this mass matrix M equal to 1 0 0 1 and the stiffness matrix K equal to G by L 3 minus 1 minus 1 1. So, I can find this A matrix. So, A is nothing but M inverse K. So, you just find the inverse of M matrix. So, inverse of this unit matrix is also you can find it same. So, M inverse K you can find. So, this M inverse K you can find it equal to G by L. So, this will be equal to 3 minus 1 minus 1 1 because this M inverse is the unit matrix. So, you multiply with this K matrix. So, it will remain same. So, this becomes G by L 3 minus 1 minus 1 1 and so you can find A minus lambda I. So, A minus lambda I will become, so A minus lambda I you can write will be equal to 3 G by L minus lambda. So, minus G by L and this is minus G by L and this is minus G by, this is G by L minus lambda. So, the determinant of this will be equal to 0. So, you have a quadratic equation. So, this equation becomes lambda square this multiplied this minus this into this. So, this will give rise to lambda square minus 4 G by L lambda plus 2 into G by L square equal to 0. So, from this you can get lambda 1 equal to 2 minus root 2 G by L and lambda 2 equal to 2 plus root 2 G by L. You note that this lambda 1 and lambda 2 what you have obtained using this generalized coordinates theta 1 and theta 2 and using this coordinate system x1 and x2 are same. So, the generalized, so whether you are using this x1 x2 as generalized coordinates or theta 1 and theta 2 as generalized coordinates, they will lead to the same natural frequency because the natural frequency of the systems are same. So, you can find now the normal mode. So, the normal modes can be obtained, this is x1 x2. So, you can find this x1 by x2 at lambda equal to lambda 1. So, from this first expression, so from this expression you can write, so already you know this A minus lambda y x1 x2 equal to 0. So, 3 G by L minus lambda into x1 minus G by L x2 equal to 0. So, this x1 by x2 will be equal to G by L by, so this term, so this G by L by 3 G by L minus lambda. So, you can write this x1 by x2 is nothing but G by L. So, this is equal to G by L by 3 G by L minus lambda. So, for lambda equal to lambda 1 you can substitute equal to this lambda 1. So, this is reduced to, or you can find it equal to 4 1 4 2. Similarly, x1 x2 lambda 1 lambda equal to lambda 2 will becomes G by L 3 G by L minus lambda 2. Already you know your lambda 2 equal to 2 plus root 2 G by L. So, this becomes minus 2.4142. So, from this you know that when x1 equal to 1 or when x2 equal to 1, your x1 becomes minus 2.4142 and when in the first mode when x2 equal to 1, x1 equal to 0.4142. So, you can draw these modes. So, if you draw these modes, so the first case you can see that the first case the opposite way also you can do. So, when x1 becomes 1, x1 becomes 1, so this x2 will becomes, so when x1 equal to 1, x2 equal to 2 point, so this x2 equal to 2.4142, that is 1 by 0.4142 equal to 2.4142, and for the second mode you can see that, so when this is equal to 1, so this becomes, you can find this. So, you can see that this becomes minus 0.4142. So, x2 becomes minus 0.4142. So, you can see that inverse of this 2.4142 equal to 0.4142. So in the first case they are in phase and in the second case they are out of phase. So in this way you can find the normal mode of a system by using the eigenvalue method also. So first, so the steps are, so first you write the equation and write the mass matrix, write the stiffness matrix. So now you find the A matrix, so A matrix equal to M inverse K. So after finding A matrix, so you just find the determinant of A minus lambda I. So from that you can find the value of lambda. So in this case you will get 2 value of lambda, and lambda is nothing but square of omega 1 or omega square. So from that you can get the normal mode frequency of the system. So to find the free vibration response of the system, so you can use the superposition theory, or you can assume that the free vibration response of a system is the summation of the normal modes. So taking those summations and using the initial conditions, you can find the free vibration response of the system. Now I will tell you about the coordinate coupling of a system. Already I told you the static coupling and dynamic coupling of the system. So let me take some example to show you that how by changing this coordinate system you can find, or you can make the system uncoupled or coupled, or you can make the system statically and dynamically coupled or uncoupled. So let us see this coordinate coupling of the 2 degree of freedom system. So coordinate coupling. So let me take the simple example of that lathe machine previously I have told. So in that case I can assume that lathe machine consisting of a headstock and tailstock as a single mass. I can assume this as a rod. I can assume this as a rod with mass concentrated at some position. So I am assuming that the mass is concentrated at this position G. So this is the position G where the mass is concentrated. I can assume this the bed of this lathe machine. So this is the lathe machine you can take. So with a headstock and tailstock. So this is the headstock, this is the tailstock I am taking. So the mass, I am assuming that the mass is concentrated towards this headstock. So this is the point G. So I can take different coordinate system now to find the equation motion of the system, and I will show you by taking different coordinate systems you can make the system coupled or uncoupled, or you can make the system statically and dynamically coupled and uncoupled. So let me take a point C here and I will define. So this is the reference line. So I can take a reference line, or initially let it is at this position. Now due to this vibration, so it has come to this position. So this is the point C which I am taking as the where I am taking the coordinate frame. So this point C will have a displacement xc and rotation theta c. So it will rotate by an amount theta c. So let this distance between C and E is E, that is eccentricity. So I can take this as E. So as I am assuming this theta c to be very small, so these are the, so I can take this spring or the spring force to be vertical. So this is K1 I am taking, this spring constant is K2. So this distance, the displacement of this point and displacement of this point I can take, and I can find the equation motion, or so the displacement at this point. So this is theta. So displacement of this point let us find. So displacement of the different points we will find, and let us draw it clearly and do it again. So let me take the line like this. So this is xc, and I will draw a line parallel to this, and this is the forces acting on these points. So this is the G point. So the inertia force will act at this point. So this point will have a acceleration of, so this point has a acceleration, the C point has a acceleration of xc double dot. So this point which is at a distance E from this, and this angle I am taking it is theta c. So this point will have a displacement relative to this equal to E theta c. So acceleration will be E theta c double dot. So this point will have a acceleration of x c double dot plus theta E theta c double dot. So if I am taking m as the mass of this bed, then I can write the inertia force equal to m into x c double dot plus E into theta c double dot. So this point will have, this is k1, so this is k1, so this distance equal to, x c. So this is the final position of this. So as this is the final position, okay, so this is the final position, the force will act here and here. So this distance equal to, so this is x c minus, so let me take the distance between this and this equal to, so this is L1 and this is L2, so I can take this is L1, this is L2. So this will be equal to x c minus, so this total distance is x c, so this will be, so this distance equal to L1 theta c down theta c. So the spring will have a displacement of x c minus, so this will have a displacement of x c minus L1 theta c, and this spring will have a displacement of x c. So this is x c, so this is the additional displacement it will have, so this is x c plus L2 theta c. So the force here will be equal to k2 into this displacement, that is x c into L2 theta c, and the force here equal to k1 into x1 minus L1 theta c. And the inertia force acting at point G will be equal to mass into x c double dot plus E into theta c double dot. So in addition to this, at the point here, let me assume that the inertia, rotational inertia equal to J c. So I can write J c. So this point will have a rotational inertia force equal to J c into theta c double dot. So I can write the equation motion by doing the force balance. So by doing the force balance, I can write m into x c double dot plus m e theta c double dot plus k1 into x c minus L1 theta c plus k2 into x2 plus L2 theta c equal to 0, and taking the moment about this point C, I can take the moment about this point C. So moment about this point will be equal to 0. So moment of all the forces about this point I can take. So this will be equal to J c into theta c double dot plus this mass into, or this inertia force into this distance E, and then this force into this distance and this force into this distance. So the equation I can write in this form. So it will be equal to J g theta c double dot, inertia force will act at the mass center, that is at G. So J g I can write, so J g theta c double dot plus, so plus I can write it equal to m x c double dot plus m e theta c double dot. So this into distance E minus this k1 into x c minus L1 theta c into, so this is at a distance x1, this is at a distance L1, as I am assuming this theta 1 to be small. So this distance I can take it as L1. Similarly, that other support distance I can take it as L2. So plus k2 into x c plus L2 theta c into L2 equal to 0. So these are the two equations I obtained for this lathe machine. I can write, I have expressed the motion in terms of x c and theta c. So the generalized coordinates I have taken are x c and theta c are the generalized coordinates I have taken. So I can express these two equations in terms of the matrix form also. So in matrix form I can write it like this. So it becomes m e j into x c double dot theta c double dot plus k1 k2 k1 plus k2 k2, then so this is k2 L2 minus k1 L1. So this is k2 L2 minus k1 L1. This is k1 L1 square plus k2 L2 square into x c theta c. So this becomes 0 0. So in this case you just observe that by taking a coordinate system at position c, so I am taking a coordinate point at, or I am describing the motion of the system by taking a coordinate system here, that is the displacement, translational displacement x c and rotational displacement theta c. So I am obtaining a equation motion where both the mass matrix and stiffness matrix are coupled. So the system is both dynamically and statically coupled. So I can make the system uncoupled by taking the coordinate system at other places also. So let me take the different conditions. So for case 1 let us take E equal to 0. That means if I will take the coordinate system at point G instead of taking at point C. So if I will take the coordinate position here and I will describe this motion in terms of x and theta, rotation displacement x here and rotation theta here. So in this case this equation will reduce to, so this E equal to 0. So this mass matrix become M0 and 0 JG, but the stiffness matrix will be unchanged. So in this case the system will reduce to, or system will have a mass matrix, uncoupled mass matrix. So the system will be dynamically uncoupled. So you will get a dynamically uncoupled system. Now you see that if I will take this k2 L2 equal to k1 L1. So if I will take k2 L2 equal to k1 L1, so this part equal to 0. So this term will become 0 and this term also will become 0. So in this case you will have a stiffness matrix where k1, so stiffness matrix will be k1 plus k2 0 and 0 k1 L1 square plus k2 L2 square. So this is also statically uncoupled. This becomes statically uncoupled if I am taking, so if I am taking this k2 L2 equal to k1 L1. So if I will take L1 equal to 0, that means point C coincide with the left end, then the equation motion will become, so you can see that L1 if I will take it 0, so in that case this equation will becomes like this. So it becomes ME, then this ME J XC double dot and this then theta C double dot plus K1 plus K2 L2 K2 L2 square theta into XC theta C equal to 0 0. So this case also the system is both dynamically and statically uncoupled. So by changing this position of the coordinate system, you can make the system a coupled one or uncoupled one, or you can get statically and dynamically coupled or uncoupled system. Already I told you the coordinate system for which you are getting a system which will have both dynamically uncoupled and statically uncoupled equations, or that is mass matrix is uncoupled and stiffness matrix is uncoupled. That coordinate system is known as the principal coordinate system. So by changing this position of this coordinate system, you can get a coordinate system, or you can get the equation motion where it will be reduced to a set of coordinate system which will looks like this. So M11 0 M22 x1 double dot x2 double dot plus K11 0 K22 x1 x2 equal to 0 0. So these two equations, so if they are uncoupled, dynamically uncoupled, and this is statically uncoupled, so I can write this equation in this form. So this will becomes M11 x1 double dot plus K11 x1 equal to 0, and second equation becomes m22 x2 double dot plus k 22 x2 equal to 0. So, you can see that they have reduced, or they are reduced to a set of two equations which are the first order equations, which are the equations you have already studied for this single degree of freedom system. So, you can solve these equations very easily by writing x1 equal to, so x1 will be equal to, so this x1 I can write equal to a sin omega 1 t plus psi 1, and this x2 will be equal to a2 sin omega 2 t plus psi 2, where this omega 1 is nothing but root over k 11 by m 11 and omega 2 is root over k 22 by m 22, and this psi 1 psi 2 and a1 a2 can be obtained from these initial conditions. So, if you are able to reduce the equation motion to that of a equations where both the mass matrix and stiffness matrix are uncoupled, then you can convert these equation to a set of single degree of freedom system equation, and already for single degree of freedom system you know the solutions and you can find the solution of the system, or you can find the normal mode of the systems very easily. So, now let us study about a system with damping. So, 2 degree of freedom system with damping. So, previously we have studied the system without damping. Now, let us take a system with damping. So, in this case I can draw the system like this. So, let me take the same system what I have taken before, but here I will introduce some damping in the system. So, this is the mass, first mass. So, let me take a damper here. So, again another damper I can take it here, and so this is the third damper I have taken. So, it is connected to this constant one. So, now you can derive this equation motion for the system. So, this is, I will take it is k1, this is mass m1, this is mass m2, and this is c1, this is c2, this is stiffness is k2, this is k3, and this is c3. So, you can take the displacement of mass m1 as x1, or I can take a generalized coordinate x1 and x2. So, x1 is the displacement of mass m1 and x2 is the displacement of mass m2. Either you can use Lagrangian principle, or you may use this Newton's second law to derive this equation motion. While using this Lagrange principle, you can take this dissipation energy. So, dissipation energy in the first case it will be equal to half c1 x dot square x1 dot square, and in the second case it becomes half c2 into, so in the first case your d1 equal to half c1 x1 dot square, and your d2 equal to half c2 x2 dot square. So, the equation motion, if you are using this Lagrange principle, so the equation motion you can write in this form. So, your equation motion will reduce to, your equation motion is reducing to m1 0 0 m2 x1 double dot x2 double dot plus k1 plus k2 minus k2 minus k2, this is k2 plus k3 x1 x2. Already you got these expressions, and if you are adding damping, now your equation is reduced to this. So, this becomes c1 plus c2 minus c2, this is minus c2, then this becomes c2 plus c3 into x1 dot x2 dot equal to 0 0. So, by adding this damper in the system, your equation motion is just changed, just you have added this term to your previous equations what you have obtained before. So, now you can assume a solution normal mode solution in this form. So you can assume your x1 equal to a1 e to the power st, and x2 also you can assume it equal to a2 e to the power st. So you just see that in case of normal mode vibration, we are assuming the system to be vibrating with same frequency. So I have taken this s is the complex number. So you can take the solution in this form a1 e to the power st and x2 equal to a2 e to the power st. So if you substitute this in this equation, so you can write this equation in this form. So you can write this equation in this form. So it becomes m1 s square plus c1 plus c2 s plus k1 plus k2, then minus c2s minus k2, and this becomes minus c2s minus k2, and this becomes m2 s square plus c2 plus c3s plus k2 plus k3. So this multiplied by, so this into a1 a2, so this into a1 a2 equal to 0 0. So as this multiplied a1 a2 equal to 0 0. So for non-trivial solution, the determinant of this, the determinant of this will be equal to 0. So if you find the determinant of this, so this will reduce to a fourth order equation. So this equation you can write in this form. So this equation becomes m1 s square. So if you multiply that thing, this becomes m1 s square plus c1 plus, or you can find, so this multiplication this minus this into this equal to 0. So you will have 4 roots. So from these 4 roots you can find the solution of the system. So using those 4 roots you can find 4 frequency, and using those frequency you can write the solution of the system. So you can write your x1 equal to a1 e to the power, so you can write x1 equal to a1 e to the power s1t plus, or a11 s1t, a12 e to the power s2t plus a13 e to the power s3t plus a14 e to the power s4t. And similarly you can write x2 equal to a21 e to the power s1t, a22 e to the power s2t plus a23 e to the power s3t plus a24 e to the power s4t. So you can see that this a1, a11 or a1i and a2i are arbitrary, and using these initial conditions either you can find ai or a2i. As a2i and a1i are related, so you finding this first a1i, you can find a2i, as you know that this a1i by a2i are nothing but this is equal to, so from this equation you can find, so from this equation you can write a1i by a2i is equal to c2si plus k2 by this m1 si square plus this c1 plus c2 si plus k1 plus k2. So in this way you can determine the response of a system with damping. So next class we will take one example, solve this damped system, and also we will study about the force vibration of 2 degree of freedom system.